This is the Introduction to Advanced Algebra 2. I'm Mr. Stark, and I'm excited to invite you to the very first lesson of the very first unit of this advanced math course. It includes some great topics that are prerequisites for a pre-calculus course, because Advanced Algebra 2 picks up where Algebra 1 left off, and it finishes in the same way that pre-calculus does. Those topics include real numbers, Cartesian coordinate system, which relates to your work in geometry, linear equations and inequalities, woo, lines in the plane, which, you studied parallel and perpendicular lines, the different ways to solve equations, complex numbers, and more. The very first topic, which is real numbers, is split up into two parts. Lesson 1A, which is all about real numbers and inequalities, which we'll start in just a moment, and Lesson 1B, basic properties of algebra. For Lesson 1A, you can follow along using this document. So let's get started. Let's start with the vocabulary of number sets. The first number set we'll talk about is the set of real numbers. We'll do a definition, not an example. It's a number that can be written as a decimal. Some examples include 5.0, negative 1.5, and 0.223. The next set is called natural numbers, and it's called that for a reason. Think about it. When humans first started counting, they looked around for something to count, and they had their hands right in front of them. They decided, aha, I'll count on my fingers. 1, 2, 3, 4, and so on. Now we have whole numbers that includes 1, 2, 3, and so on, but it also includes a special number, the number 0. Integers include whole numbers, but they also include the negatives of those whole numbers. So I would write negative 3, negative 2, negative 1, 0, 1, and 2. The last set for our table is rational numbers. Rational numbers are special in that the way that we define them is a ratio of two numbers. Ratio is included in the word rational, so it makes a lot of sense actually. So it's A divided by B such that A and B are integers, so it could be positive or negative values, but the denominator cannot be 0. B cannot be equal to 0 because then we would have an undefined number. Some examples of rational numbers include 1/3, 1/2, 0.75, and many, many more. If we write 1/3 as a decimal, we get 0.333333 repeating. If we write 1/2 as a decimal, we simply get 0.5. So the decimal form of a rational number either terminates or is infinitely repeating. Another number set that we can talk about is irrational numbers. And irrational numbers don't terminate, and they're not infinitely repeating. Examples of that include pi or e or phi. In a moment, we'll use the space on the right to visualize these sets in a Venn diagram. Before we do that though, if we consider any two numbers that are a part of any of the sets that we just talked about, we can order those two numbers on a number line. Let's call those numbers A and B. This means A is greater than B. And this means A is greater than or equal to B. Then we have the other ones. This means A is less than B, and this means A is less than or equal to B. Okay, so we know what the inequality symbols mean, but I want to tell you something special about real numbers. One of these three situations is true. Either A is greater than B, A is equal to B, or A is less than B. That's called the trichotomy property, and it provides a structure for us to solve equations and inequalities. Okay, now let's draw that Venn diagram I mentioned. I want you to draw a square, a large one, and label it numbers at the top. Inside that square, draw two rectangles, one for real numbers, that should take about 2/3 of the space, and one for imaginary numbers. We didn't talk about that, but that'll take up 1/3 of the space. So label those real and imaginary. Now let's work the real rectangle. Inside the real rectangle, I want you to draw two more rectangle type shapes. They could be curvy. One that's called rational, and that takes up about 3/4 of the space. And then down at the bottom, the other one is called irrational, and that's just fairly small, just enough to put 3 symbols. Inside rational is the number set integers, so draw another rectangle or ellipse inside integers. And then finally, one more inside integers that's called whole. And at the very center of that, we'll label natural. So your drawing should end up looking like this. And on the far right, the rectangle for imaginary, we're only just writing a few symbols in there. So those symbols could be I or I squared, or just a square root of a negative number. Pause the video now if you need to finish up your sketch before the next idea. Now let's make sure we understand intervals and interval notation, because many times the answer to a question is not just a number, it's an interval. Notice, below the second star it says unbounded intervals. That's what this slide is all about. But it says refer to booklet cover for bounded intervals. On the next slide, you'll see those, and you can pause the video if you like. So let's fill out this chart. On the left, we have interval. In the middle, we have inequality. On the right, we have graph. So we'll just understand the interval in 2 other ways. The first unbounded interval is from a to infinity, inclusive of a. So we use an open bracket. That means x is greater than or equal to a. The graph for that is just a number line, and at a we use an open bracket and fill in everything to the right, shade it in. Now in Algebra 1, we may have used a circle or a hole and fill it in because that means inclusive. But in Advanced Algebra 2 and Pre-Calc and beyond, we use brackets. The next unbounded interval is from a to infinity, exclusive of a. So we use an open parenthesis, that's the singular word for parentheses, and that means x is greater than a. So x can't be a. The graph for that is a number line, and at a there's an open parenthesis, and we shade everything in to the right, because again, infinity is to the right. The remaining 2 intervals include the number b, or the letter b. And just so you know, when we talk about intervals and we're using the letters a and b, we usually think of a as the beginning of the interval and b as the end of the interval. It might actually make more sense if z was the end of the interval, right? Like the letter z, so that we have all these letters to put in between, but z is used for the z-axis. So I don't know what to do about that. The next unbounded interval is negative infinity to b, inclusive of b. So we use a bracket. The inequality for that is x is less than or equal to b. And the graph is a number line that ends at b with a bracket. So I'm putting b more on the right side of the graph. Then I shade everything to the left of b. And the final unbounded interval is negative infinity to b exclusive of b. So we use an open parenthesis next to b. That means x is less than b. And the graph for this one looks very similar to the last one, except we have a parenthesis where b is. That opens to the left, and we shade everything in to the left of that parenthesis. Let's look back at the intervals now and make sure we know what unbounded means. For the first 2 intervals, notice that infinity shows up. X can be greater than or equal to a, or greater than a, all the way to the right. So we include all of these positive values that go up until infinity. So it's unbounded to the right. It keeps going. Notice in the bottom 2 intervals that negative infinity shows up. So once we plot b on the number line, we include all of the values to the left of b. One's inclusive, one's exclusive of b, but both of those include all of these crazy negative values, and maybe even some positive ones that are near b or something, depends on what the value of b is. But it's unbounded to the left. X can be any of those values all the way left on the number line. Okay, let's finish with this example. Describe and graph the interval of real numbers for -3 is less than or equal to x is less than 5. So the first thing we want to do is try to write this in interval notation. But notice that this particular inequality is bounded, meaning there's no infinity on the left or on the right. So it's a little different, but we can do it. X is greater than or equal to -3 means that we would use a bracket next to -3. So we start with an open bracket, -3, and then a comma, and the fact that x is less than 5 and not equal to it, we would use a parenthesis. So bracket, -3, comma, 5, parenthesis. One way we could read that interval notation is x is in between -3 and 5, and inclusive of -3. To graph that interval, all we need to do is sketch a number line and plot -3 towards the left, 5 towards the right, draw a bracket at -3, a parenthesis at 5, and shade everything in between. And again, if we were in Algebra 1, we'd have a closed hole at -3 and an open hole at 5. That is the end of Lesson 1A, Real Numbers and Inequalities. Thank you so much for watching, and be sure to check the description for more information and add a comment below if you like. Thanks.